Hello, everyone. My name is Deep, and I'm a co-op at Loyalty One, and I study at University of Waterloo. So it's a student design team I'm part of, University of Waterloo. It's called Waterloop. So I'll be talking a bit about like Hyperloop and how we are a student design team competing in a competition. So a question like, what would you do if you could travel at the speed of sound, like from Toronto to Ottawa in about 20 minutes? That's kind of the stuff we are imagining as a Hyperloop. I'm not sure how many people know about Hyperloop. It's like another mode of transportation. There's an idea by Elon Musk back in 2013 about Hyperloop, and that's kind of how the team started, and that's what we're working on. I'll be talking about that. So if Hyperloop exists in future, so you will be able to theoretically go from Toronto to Ottawa in about 20 minutes or Toronto to Waterloo in about 10 minutes. That's amazing because I'm from Waterloo, I'm working in Toronto. So if I go back, it's about 3 hours, so that'd be amazing nice. And that's kind of the idea, that there hasn't been innovation done in transportation for a while. We start with boats, then automobile, trains, planes, and then there's a need for another mode of transportation that can get you that fast. Hyperloop, it could directly go at a speed of sound. That's 12,550. And if you could do that, that's pretty fast. So if some people don't know what Hyperloop is basically a vehicle traveling in a vacuum tube. The reason for the vacuum tube is that you eliminate all the air or any sort of friction or force that's exerting on your vehicle to go faster. I'll just show you a little video about the tech and how it works kind of thing. It's pretty basic info.
Elon Musk's revolutionary transit system, the Hyperloop, is proving to be the future of travel. But how exactly does it work? From its tube track design, it's easy to assume that the Hyperloop would operate like the vacuum tubes at bank drive-thrus or old mailroom systems. However, it has 4 key features that set it apart from these vacuum tubes in high-speed train tracks. The passenger capsules aren't propelled by air pressure like in vacuum tubes, but by electromagnetic motors, similar to ones featured in Tesla cars and railguns. It's aimed to travel at a top speed of 760 miles per hour, rocketing between Los Angeles and San Francisco in around a half hour. The tube tracks do have a vacuum, but they're not completely free of air. Instead, they have low-pressure air inside of them. Most things moving through air tubes will end up compressing the air in front, thus creating a cushion of air that slows the object down. But the Hyperloop will feature a compressor fan in the front of the capsule. The compressor fan can redirect air to the back of the capsule for additional propulsion, but mostly the air will be sent to the air bearings. They're ski-like paddles that levitate the capsules above the surface of the tube to reduce friction. The tube track is designed to be immune to weather and earthquakes. It's also designed to be self-powering and unobstructive. The pillars raising the tubes above the ground have a small footprint and can sway in the case of an earthquake. Each of the tube sections can move around flexibly if the terrain shifts because there isn't a constant track that the capsules rely on, and solar panels on the top of the track supply power to the periodic motors. With these innovations and a completely automated departure system, Elon Musk dreams of the Hyperloop being the fastest, safest, and most convenient form of travel in the world.
So the idea is that you're wrapped in a tube, that you're isolated from the environment, plus you don't have the air resistance, plus since we're using electromagnetic motors, there will be no friction in terms of the motor because yours is non-contact propulsion and non-contact. So as our team, we're University of Waterloo. It's a student design team. We are over 150 people. We're the only Canadian team that's competing in a SpaceX Hyperloop competition. That's a student competition that lets students go to California and SpaceX headquarters to compete in a competition to show who has the fastest pod in the world. And so far we've been top 15 in the world. And every year we go, and that's kind of our team. We have 150 plus student, engineering, math, almost every faculty. And as a team structure, we have a software, electrical, mechanical standard, but I'll be talking mostly about the software team. There's like embedded systems, dashboards, and communication. I'm the software lead for the team. And in terms of our stack kind of thing, we have like embedded systems at the bottom, which is all the core controllers of the pod that controls actuators, pull sensor data. But then there's a middle part that's kind of the central processing unit, the brain of the pod. We use Raspberry Pis for that, with a custom software on top of that communicates with our servers, that's desktop server and dashboard. The idea is that we can control our pod from a dashboard that's not in the pod, and then we can see how the pod's going in the tube. And we use Node.js as a server for Raspberry Pi and a desktop server. with WebSockets connecting to the desktop server. The reason for using JavaScript or Node.js is that we're a student team. We're for mostly first, second, third year students, and JavaScript is like an easy language to pick up, and plus it's a nice framework that lets us do things. For Dashboard, we do use React. That's pretty much like an easy development for us. We only get about 4 months to build something. It's a very intensive timeline, and then we really need to build up a software. So in terms of our competition, there are 3 phases. We have a prototype phase where we design the pod. That's 4 months of designing, just not building anything, but more like making sure all the designs are correct, mostly mechanical designing, and then software as well. Then there's a manufacturing, 4 months of manufacturing. Currently, we're in the manufacturing phase for next year's competition. Then there's a testing phase where we go and test if a pod will handle every sort of situation that we'll encounter in the tube. I'll show you a bit of video about a team that competed last year when we were at a competition. It was a world record for Hyperloop at that time. Like this is just 324 kilometers per hour. The plan is to go like at least more than 3 times like this, and if we can do that, like this is almost as fast as high-speed rail. This is just a second or third iteration actually, and I think with multiple iterations we can easily, like this year competition probably will reach 500. I believe some team would do that. And as our pod as well, we have doubled their speed every year. Like the reason for that is that we're using fully non-contact systems like electromagnetics. As the more and more research is being done in electromagnetics, we can figure out a faster way to go. I'll explain a little bit about how our pod works in a bit. So like our pod, so we call it Goose. We have a Goose 1, Goose 2, Goose 3. So first competition, we started with Goose 1. It was a pod, the first iteration of the pod wasn't that fast, 50 kilometer per hour, just kind of like initial test. But our big breakthrough was that we were one of the first team to do air levitation. Our pod was levitating with air, as in air bearings. So we built up on that one, Goose 2. We went around 110 kilometer per hour. As I said, we doubled. And then for that one, that pod actually, one of the good things about the pod was it was fully non-contact from braking to propulsion to levitating. So with that, we were able to travel that fast with non-contact. With Goose 3, we're again building up on that one. But now we're introducing something called linear induction motor. It's a industry standard of a motor that's a rotor on top with electromagnetics. The idea is that it's one of the first team to build it on top of the pod. Most of the linear induction motors in the world are in a track, and those tracks are really expensive to build. What we are doing is flipping it up and putting the motor inside a pod and using a track as a rotor. Tracks will be like a normal beam of metal or aluminum, and then we'll have our pod as electromagnetic motor. And if we can successfully do it this year, this will be like one of the few pods or one of the few linear induction motors that are built in a thing. And we'll be competing in Hyperloop competition with that. And we have a design for that, obviously, we just have to build it. And that's us in California. We do take our pod there. Then there's Elon Musk and then SpaceX competition. So it's like a full-on event that year. And that's where they do our testing and everything. We go through rigorous testing, make sure everything's correct. They mark us like they're marking a rocket or everything. Like every bolt has to be correct. And that's I'll show you a bit of a levitation, how it looks like. I'll start around the time. Yeah, since we're like one of the only Canadian teams, we do like to show off like Canadians. We bring our flags and everything. I'll show you in a bit. It's good to like, it's an international competition, Germans versus Canadians versus all that. So it's kind of cool. That's what was revealed in the first competition when we did the levitation. So the thing about our pod was that I could stand on it, it would still levitate. So our pod was about 150 kilograms, and that heavy pod, once you're levitating, you can move with the pinky. So at that time, if you're levitating a pod, doesn't matter how heavy it is, it's very easy to move. And that's what kind of the levitation thing we get. Using air is very easy, it's cheap air. People use magnets to levitate as well. With magnets are expensive and they're heavy. With air, we have air casters and we have air. Potential ideas that in a vacuum chamber, whatever the air that's left behind, we'll reuse that for air casters. And this was a great proof of concept for the first time that we could do levitation, and it's very effective. So in a run, we were levitating for the whole time. And in case there's a problem, we have wheels that it drops down to wheels, but we're levitating pretty much the whole time. So that's us in California. Again, as I said, we do like to show Canadians. We are the only Canadian team competing at the competition. That's our team. It's a huge group. It's an expensive competition too. We are funded by university, different sponsors. So it's a lot of work. And that's again our team. We're showing us at the competition, Falcon. But yeah, this is a competition fourth. Our team will be going there. And idea is that current record is about 400 kilometers per hour. The idea is to break that this year. And our team's motto is to have non-contact. We don't want to try any contact propulsion system, even though those are the easiest to do because they've already been done. So our team has spent a lot of time to research and all that stuff to figure out how to work with electromagnets more and more. As a team, we are undergrad students. We are first year, second year, third year, around fourth year. That's about it. We have some masters, but that's what we'll be doing. And that is a Hyperloop will be, we are pushing the boundaries of Hyperloop. One day they will be reality. I believe like in 5 to 10 years, maybe not carrying people, but carrying cargo. It will be that we can make travel so much faster than trains are. Trains are very inefficient. They're outside. They're on tracks that are not predictable. If you are having closed system, ecosystem, plus with vacuum chambers, you can go much faster and more predictable times. One day, travel will be possible with humans as well. They're just complications in terms of how humans fit in vacuums and all this stuff, infrastructure issues. But yeah, that's our team. You could check us out, waterloop.ca. You can follow us on Twitter or Instagram or anything. But yeah, that's what we do. And there aren't a lot of teams in Canada who do it or in the world. This Hyperloop one, the bigger name, probably you've heard about it. And so more and more companies are kind of coming in the market. But the idea is to make Canada one of the forefront in this type of technology because a lot of countries don't have a team like that. So that's kind of the University of Waterloo, our role, or as a team, we're really proud of. Thank you. That's